Okay, this video is part of the calculus series on vectors, and we're talking now about vector-valued functions now that we've defined what a vector is. And we're going to put together a number of things from different parts of the course here to define something that's a really powerful structure and a key part of what we do next year in Calc 3. We know how to represent a plane curve using parametric equations, right? The idea that we can define x and y in terms of a parameter t. Maybe it represents time. And that means you can plug in different times and you get x and y components to plot that. You have a trajectory along some sort of a plane curve like this to show how an object is moving as time progresses through the xy plane. And then separately, we define how vectors work, which is that a vector is directed a direction, like a translation, where we have an amount of motion in x or y, a translation in x and y that we combine together into one object here. So we can put these two ideas together by saying we can take a parametric set of equations where x is a function of the parameter t and y is a function of the parameter t, and put those x, y locations in as the xy values for a vector. So if we have essentially x and y of a vector that are functions of a parameter, then this is called a vector-valued function. And the symbol that we usually give for that, we usually use t for the parameter, just like we did for parametric equations. And we usually use r here. I'm not exactly sure why, but we use r, and the result is called a position vector or a vector function or a vector-valued function. So what that means is that this is like a function. So the domain of this function is t, right? It could be time, but it's a scalar number of some kind. And then the range, or what comes out, the range, the output is a vector. So you plug in a parameter and the x and y parametric equations convert that into x and y locations that we combine into a vector, and the vector itself is the output. So this is called a vector-valued function because you get a vector as the output of the function. All right, so for example, let's say, that we have this particular structure here. This is the vector-valued function definition. We can call it a position vector. The output is a function that we're going to label r of t, a vector r that is a function of t. And you can plug different t values in here. So for example, if I plug 0 in for t, I would get -4 for x and 0 for y. And that locates a specific point, right? X is -4, y is 0. This point is when t is 0, right? The difference is, instead of it being parametric equations, we now are talking about this as a vector. So what is that vector? Well, a position vector is a vector that has its initial point at the origin, and it points to the location, right? So this r vector, which I could write this as r, the r vector at time 0 is this green vector right here. It's a vector that goes from the origin to a location. It's pointing to the location -4, that's a coordinate pair, but the value of this vector is angle bracket -4, 0, because starting at the origin, we're translating -4 in the x and 0 in the y to get to that location. And this is all happening at the input time of the vector 0. If I go to some other time, like let's say time is 3, let's say t is 3 and t represents time, if you plug that in, you get an x component of 5 and a y component of -3/2. And that means that r at time 3 is the vector 5 3/2. That is a vector that starts at the origin, goes 5 over and 1.5 up, right? So it's this vector, that's the vector r3. And it's pointing, its values are 5, 3 in angle brackets. It's pointing at the coordinate location, regular brackets, 5, 3/2. Okay, so the notation, the angle brackets indicate the vector's x and y components. If we're talking about a position vector, that's what the symbol r is saying. That means we're starting at the origin. So we are actually, the endpoint is the same numbers as the x and y components. All right. So since it's a function, it means it has a domain. And if you're trying to determine the domain of a vector-valued function, you start by assuming that the parameter can take any parameter value from negative infinity to infinity, and then you remove from the domain any parameter values that are not allowed because they cause any of the equations to be undefined. So the function itself definition might restrict the domain. They may say, oh, this is only defined for t's from -2 to 3. That could establish the domain. If it's a real world problem, the parameter t could represent time, in which case negative values might not make sense, although you shouldn't necessarily assume that. Maybe negative time does make sense in a particular problem. And then, of course, anything that makes the function undefined, like dividing by 0, even roots of a negative, like a square root of a negative, or logarithms of negatives or zeros. So let's say we want to find the domain of this vector valued function. So we start by assuming that everything is okay from negative infinity to infinity. There's no definition that tells me what the domain is, so I'm assuming that. That restricts the domain in any way in the definition. There's no real-world problems. This isn't a real-world problem. But I do know that I need to avoid some things here. Like I have to avoid the value t is 1, because t is 1 would cause the denominator to be 0. So I have to avoid the value 1. That one I have to avoid. And then for this, I can't take a square root of a negative. So let's see, square root of 4 minus t squared. I can't let 4 minus t squared be negative. It can be 0 though, so it can be greater than or equal to 0. So if I were to, let's see, subtract 4 from both sides here, and then multiply by a -1, that would change the order of this. And then that means t squared would have to be less than 4, less than or equal to 4. So I think that's going to end up being, well, let's see, the values. So you can try an approach like that, but if that's confusing, you can also do this. Where is this 0, right? Where this starts to transition from okay to not okay. Well, that would be 4 minus t squared equals 0 when t is equal to or -2. So maybe what I could do is I could go to -2 and 2 and just test some values here. So let's test values in each of these regions. Let's see, in this region, -3, what if I were to put in a -3? I would get 4 minus -3 squared, which would be square root of 4 minus 9, which is the square root of negative. So that's not okay. So that value is not okay, and that means all these values are not okay. We're not going to be able to include those. What about the -2 itself? If we tested that, that would be the square root of 4 minus -2 squared would be the square root of 0. Square root of 0 is fine. So I can include that. That's an okay value. What about the values between -2 and this value 1? Well, if I pick a value here, like let's say 0, for example, that's a test value. 4 minus 0 squared would be the square root of 4. That's perfectly fine, which means that and all the other values in there are fine. We already know we have to avoid 1 because of this one, but these values here, like say 1.5, if I put 1.5 in there, 4 minus 1.5 squared would be a positive, so that's fine. These values are fine. The 2, if I plugged it in, would be square root of 0. That's fine. But if I go above that, then I'm going to get like a negative number in here. So these are not okay. So it looks like the values that are okay are -2 up to, but not including the 1. And then just on the other side of 1 is okay over to the 2, and that's okay. Right? So I could write this domain as t can be anywhere from -2 to 1, and then from 1 to 2, including that, or you could use, if you'd like, you could use inequalities, 1t less than or equal to 2. Okay, so just like with other functions, you have to avoid certain things that cause things to be undefined with these vector valued functions. Okay, so what about limits and continuity? If you approach a particular value of the parameter in the domain from lower and higher values, a particular vector is being approached. So let's say that I've got some curve here defined by a position vector, which was built up from x and y parametric equations. If I'm approaching, say, the number 1, so I want to take the limit as t approaches 1 of that position vector, then that means that I'm really approaching 1. Well, I have to break it into what happens if I approach from the left, and what happens if I approach one from the right. And you can see kind of graphically, these do seem to be approaching, the position vectors are approaching, this purple vector is getting closer and closer to the green vector, and this red vector, as I get closer, is getting green. So it appears that this limiting value exists, right? So all you would really have to do to find this is to take the individual limits of the x and y separately. So whenever we're working with vectors, whatever operation we're doing, we just do that separately on the x and the y components. So if I want to take this limit here, I'm going to apply that same limit to the x component and to the y component. And when we try this, if it's well behaved, we can try plugging in the number. That's 1 squared, so 1 minus 4 would be a -3 is the limiting value for the x component. And if I plug a 1 in here, it would be a half. So we're approaching that green vector, which is -3 for x and 1/2 for y. Right? And a vector value function can be said to be continuous if the function is defined for all the perimeter values and the limit exists as we approach all those values. Right? So the reason we aren't going to do direct limit problems, but we are going to say that we need the limit to define the derivative, which we do need. So recall from earlier that if you have a regular function, y is a function of x, and you have a function curve, you could be at a specific x location, plug that in and find the matching y, and then go a distance h away to x plus h and plug that in to get f of x plus h. And then the tangent line slope would be the change in y, f of x plus h minus f of x over h. And then what we would do is move these points closer together by taking the limit as h approaches 0, and that would give us what we defined as the derivative, or the slope of the tangent line, which we labeled f prime of x. Well, you can do the same thing for vector valued functions. You can say start at some parameter value, say t, go a distance h away to t plus h, and take 2 points that are on the function curve, in this case the plane curve, not necessarily a function. And then you can take the position vector to the start and the position vector to the end at t and at t plus h, and take the difference in the output, which would be the position vector to t plus h minus the position vector at t, and divide that by the difference in the input, which is the difference in the parameter, which is just h. Right? So geometrically, what is this subtraction? Right? This is like taking the t plus h vector and then taking the r vector and negating it and adding it onto the end. Right? So it's the difference between the two. I would maybe think of it as the parallelogram version. So if you have a parallelogram here, this is the sum. This is the difference going from the end one to the starting one. So this vector right here, pointing from this point on the space curve to this point on the space curve, is the r prime vector, the derivative of the position vector, right? And you could think of it as kind of like it's pointing roughly in the direction of the curve, right? And if I take a derivative of a position, it ought to represent something like a velocity, like how fast we're moving. So this kind of represents that, right? But it's not perfect because we've just gone a fixed distance h away. So we'll do the same thing as we did over here. We'll take the limit as h approaches 0. So when that happens, these points get closer and closer together, and that vector ends up becoming tangent to the position, to the plane curve, just like this line becomes a tangent line. This becomes a tangent vector. So this r prime vector is the derivative, and it's found the same way we'd take on the other derivative. And since we're doing it this way, now we could take it with the limit definition. The good news is we don't have to use the limit definition. We can just simply take the derivative of the x and y components separately. Right now, this vector, not only is it tangent, the length of this vector, the magnitude, represents how fast the object is translating along here. So since r is like a position, the derivative should be a speed, right? But it's a speed with a direction. Okay, so here's an example. Let's say that we have this position vector right here, which is the same one we've been using. How would we take the derivative? So all we have to do is, we don't have to use limits. We just simply take the derivative of this x component, which is 2t, and we take the derivative of this, which is 1/2, and we make a new vector with those components. And we call that vector the r prime vector, the tangent vector. Okay? Now, if you evaluate these at different times, so let's say we evaluate this at time -2 or 0 or 1 or 2.5, you can plug those t values into the position vector. Like let's say I plug -2 in and I get for the x component 0 and the y component -1. That's a position vector, so it's going from the origin locating this point and telling us we're at 0, -1. That's what the position vector tells me, the position. When time is 0, this becomes x is -4, y is 0. So that's telling me we're over here at -4, 0 when time is 0. And this is the position at time 1, and this is the position at time 2. These vectors go from the origin. So position vectors are always sketched from the origin to the location. Okay. But what about this r prime vector? So the r prime vector, that vector, if I plug in a position, or a parameter time like -2, I'm going to get the tangent vector at that point, which in this case is -4, 1/2. So that means if I'm at the location where I am at t is -2, I would, from that location where the object is, so position, so the tangent vector is always graphed from the object, we would go -4 in the x direction and 1/2 in the y direction. So it's a quite long green vector here. And that's telling me not only the current direction, because it's tangent to the curve, this is at this instant the direction of motion, but the length of this vector, the magnitude, tells me how fast the object's moving. Right? If you plugged in time 0, you would get to this tangent vector, this r prime vector 0, 1/2, which means when we're here, when the position vector is at -4, 0, and we're at -4, 0, right? We're currently moving 0 in the x direction and 1/2 in the y direction. So now the motion is completely vertical and it's much slower as we round this bend. Okay, this gives me the direction and speed at time 1, and this green vector tells me the direction and speed here. So based on this right here, the behavior of this object, whatever's causing this, this is coming in quickly, slowing down, and then speeding back up as we go out here. All right, so that's the geometric meanings of the position. So usually we call this vector the position vector, and we call this vector the tangent vector, because it's tangent, but it also represents speed. All right. So there are theorems that apply to all this too, and the derivatives work similarly with vectors. So if you have a position vector, and you take a derivative and you have a constant, you can move the constant inside and outside of the derivative. If you have two vectors that are added or subtracted and you want to take the derivative, you can take those derivatives independently, right, separately, and add and subtract results, just like with regular function derivatives. But if you have a scalar function times a vector, then you have to use the product rule when you take the derivatives. You have to take the scalar times the derivative of the vector plus the derivative of the scalar times the vector. And if you have a position vector that has a function inside of it, to take the derivative, you take the derivative of the components, but you have to multiply by the derivatives of the terms inside. So the chain rule applies term by term. That's probably easiest to see with this example. So this one will show how all those properties are used, or at least this last one, the chain rule. So if I'm finding the derivative of r, the position vector, the label for that would be r prime. And then for this x component, I would simply take the derivative using the chain rule. So the outside most derivative is the e, so that's going to be e with the inside copied, times the derivative of this inside, which is 2t plus 3, right? Nothing more than that. Here, this is pretty complicated. We're going to need to do the quotient rule here for this y derivative. But the nice thing is x and y are at right angles to each other, so they do not affect each other. So there's no mixing between the x and the y. So the y derivative by product or quotient rule will be low derivative of high, which is 1 over its input, times the derivative of that input, which is 2t minus 3, low d high minus high d low, which is 3t squared, over low squared, t cubed minus 4 squared. Okay, and that would be the x and y components of the tangent vector. So the nice thing is it's very consistent and behaves the way you would expect. And since we can do derivatives, integrals are just antiderivatives, which means that if you're taking an antiderivative, either an indefinite integral or a definite integral, you can do that antiderivative to each of the terms separately. So let's say we have a position vector here, and we want to find the integral of that. The symbol of that would be the integral of the r vector. And then we would take the antiderivative of cosine of t, which is sine of t, technically plus a c. And then the antiderivative here would be, let's see, that would be t to the fourth over 4 minus t squared over 2 plus another integration constant. So each independent one thing has that. Now, some people prefer to write that this way, sine of t, and then t to the fourth over 4 minus t squared over 2, and then to combine these two things together into its own vector. So this is CD, but we write that just as a vector of constants. So if you prefer, you can do that. I have over the years kind of found that people make less mistakes when they put separate constants in there. Okay. All right. So a lot of big ideas here. There's a lot of powerful ideas in here, but we'll really see how this works when we get into the next section where we do velocities and accelerations and things like that. That's the end of this video.